Okay, looks like I'm recording, so I'll go ahead and get that out of the way right now. So it's John Reagan's Board Brains Consortium and Allshay AI. And what I wanted to come to you today with is first of all, the launch of our new app, which is around here somewhere. I had to restart my computer, so bear with me here. So yeah, it is up on the Play Store. So let me go in here. You can see it's up, it's available. It's $5 right now for the next 2 weeks. This isn't a sales pitch. This is just letting you guys know it's up, it's on here. Mostly works on the phone and tablet. Works great. A lot of the testing devices were like mid, some of them lower end even, and they were still able to make multi-million parameter AI models. So that's available. It's on the Google Play Store, Allshay EasyBake AI. So you can get that now. And again, it's $5 for the next 2 weeks. And then I have to do an update for one of Google's things. And so in that update, it's going to move to a subscription model. So it'll be $5 a month. So get it now while it's non-subscription. But what I wanted to show you today is actually something I've been working on more, which is the Rust library. And this comes in right now. The whole thing, when we go in and basically look at what actually operates it, essentially is less than 200 kilobytes. And this is kind of a replacement for Python and PyTorch using Rust and my own custom MICT based uh, software library. So what happened was I started making a library for Polymorph OS because it's Rust and I needed a library or an engine to run the AIs and the models locally within the operating system. And in doing so, I realized if I made it like I did before on a regular platform, then I could just port it over easily, which is what it looks like. It's going to port right over. But this also brought me to looking at using current models with this same Rust library. And it turns out it works really, really well. We've gotten pretty deep into it. You can see here I have Gemma 2B, Gemma 7B. I have a Qwen 72B, and even a TinyLlama 1.1B. These are all unquantized. They're 32-bit actually instead of the F16, 16-bit. And the quantization I started working with, we get them down about fourfold. So we're at a i8 quantization. We're still getting the same response and quality, and so pretty much looks exactly the same, except for as you can see, say on this 72. This one's actually broken. I got to redo it. But this comes in at like 288 gigabytes, and then I broke it. You guys' stuff is so fragile. I break your thing so easily. Um, when it's quantized down, it comes in at 85.4. I'm not knocking it. I'm just saying the stuff, the models I've made, when we go in here to the models, like these ones are mine, these JARVITS models, and these are my own architectures, and they work great. Like I can beat on these things, retrain them, train them more, and they don't break. I mean, with your guys' stuff, if I stop it too soon, it's like, and I've started putting the catches in and stuff, but it's still this like, if it gets a bad training loop for some reason, it just all of a sudden freaks out. It's so funny. Anyway, so I'm able to run these now using this Rust library that I've created very leanly. So that's what I'm going to demonstrate to you now. So you can see I have those in there. They're all available, loaded. This is actually the code I'm using. So I just wanted to check it and make sure that I have the right, where is that thing? Router setup. So for the legacy, we're going to do tiered. And for the reinforcement dojo, which is actually further training these AI models, right? All these standard models. I do have to run, where is that thing? MDO. So the difference here And you can even see I've had them running. Here's some logs, files and stuff. It's pretty wild what these things say. Um, so what it is basically kind of like a version of unified RAM, but just with your standard stuff. So it's kind of like a software defined unified RAM system for building AI. And I can expand on this even further in Polymorph as it will probably work for the whole of the file system. So it's something I'm looking at right now. Um, so basically, we take and assess the whole of your RAM. So whether it's VRAM, system RAM, or whatever you happen to have, it just becomes a storage space, right? That we put stuff into and pull stuff out of. Additionally, your SSD is also a RAM-based chip, and we can also leverage that in the same way. So the faster you can get stuff on and off these things, the faster your AI can run. Literally, what I'm saying is, if you have a large enough hard drive, you can run the SSD and a high enough connection to that SSD, you can adequately run some of the largest models that anyone produces using this library I've made that is 200 kilobytes essentially. So right now what I'm going to do is, let's see if we got any of our commands left in so I don't have to type it all. Yeah, so this one's the 72B I8. This will run as what we call load from MDO. So it's loading the file. It's going to fill up the VRAM first on the 0. Yeah, it's going to fill up the VRAM first on the 0 GPU, and then it's going to drop into using RAM. And when it runs out of RAM allocation, it actually is using the SSD and the paging system within the OS. So the RAM usage is dynamic. It's not static when you're doing this chat stuff. The only time it's static is when you're actually training the model, which I'll show you one of the smaller ones. So, but this is the Qwen 72B I8 quantization. So it lets us run it a little smaller, and we'll just get that right up here. And you can't see it, but I have BTOP running on the other monitor right now. Well, maybe I could switch that. I could have added a second one, I guess. Show you. Doo -doo. You can see that is coming along, and the VRAM capacity has been reached. I wonder if I could add one while I'm recording. Never tried that. Let me see here. Oh, let me see. Screen capture. Add new one. We'll hit the little screen. Hear that? Okay. Oh, am I still recording? Yeah, it looks like it's still recording. So here you can see a little bit of what's going on. And let me just resize that a little for you. I do my best with OBS, but yeah. So we can see right here in this screen that it is right now hydrating, or sorry, VRAM capacity was reached. So you can see over here. Oh, maybe I should use it on the screen, not OBS. You can see over here that we've hit the 24 gigs essentially. And so this is a caching of all the front end layers. And what I do is the CPU and GPU work in unison um, for inference in this way. And even during training, the CPU and GPU work in unison for the training of the models. Essentially, the Rust library decouples the compute from the data itself as storage and allows us to leverage whatever you have in the most appropriate way for what it's best at. So, like right now, utilizing the GPU and the CPU, one for each set of processes, because the type of math that they're better at and how they handle that math that the AI is throwing at them is more efficient in some ways, even with the latency that we get from transferring the data across the channels on the board. So like the PCIe bus, the top card is a 16x PCIe. So that one's pretty quick. So this should take about, I think it's hydrating in about 12 minutes right now. And even response times, when you just query the 72 billion parameter model here, the Qwen model, which is essentially equivalent to a ChatGPT-4 model, um, turns out to take about 5 minutes to start responding, and then you're getting a token or a word or whatever, however you want to put it, every few seconds. So there's stuff I'm working on to reduce that time and increase its output time. But right now, the way it looks is, even though it's slow, you can still have access to a knowledge bank that is equivalent to what ChatGPT 4 is, essentially, on your home machine, right? Additionally, I can run this directly from the hard drive, from the NVMe, the SSD, right, drive, and that will allow it to work, albeit quite a bit slower, right? And in that case, it's not even about the processing and everything. It's just about the transfer speed between that hard drive and the model itself. Okay, so what I'm gonna do now, I'm gonna come back over here. We'll get this thing out of the way. Boop, I got that dropped right in. So I'm gonna, in this other window below, while that's hydrating and taking a little time, things might slow down here in the video, might get a little choppy, because this starts getting a little process intensive. So let's see what we got here. That's a 72B. I want to see, I think, yeah, it's just keeping the 72B. So I have a way that I convert these that makes them work. And so what we'll do right now is we'll go to the next smallest size model, which is the Gemma 7B. 7B, and the tokenizer is in there if I remember. Did I have one that was just for fun and to keep the sizes small? I think I have a 7B. Yeah, I8. So we'll use that one real quick. Oops. Anyway. B 8 MDO. And yes, the MDO file is required because of how I'm doing things. So this one, the i8, I thought I had it to where we could do the training with the quantized model, but there's something I messed up. I'm getting a segment fault, so I'm working on that. But we can do training with the non-quantized model, and the non-quantized model will run in RAM. It just would have a harder time with this bigger model and slow everything down. So I'm going to run the chat for this one as well, and that's going to start up. We'll put it on the. We'll put this one on the secondary card. So UID equals 1. So this one's going to run a little slower because the PCIe is slower, but it will run this 7 billion parameter model just like it's kicking up and running the other one right there. So this one here, this other window, while we're waiting for those to like hydrate and get set up here. Oh, it looks like the one is almost ready according to the BTOP output. Probably another few minutes. So this one right here, what I'm gonna do is go ahead, the one you can't see right now, because it's hidden behind the output for the other screen. This one, let me pull it up actually. First of all, make sure it's still working. Looks like I'm still getting that. Are we getting video? Video free? Hello? There we go. Okay, I think it came back. So, so I'm gonna actually like click on that one. I'm gonna turn that one off real quick, and then you'll be able to see the terminal I have up behind here. And so this one, what I'm going to do now is run the tiny little model, which is just, I just have that one. That was my first one I tested with. So we just have the tokenizer, and then we have TinyLlama underscore 1.1, 0.1. Capital B or little b. It's a thing. I always it's trying to do like a little more formatted, so it's like capital B. All my files are always a capital B. And then the folders are lowercase. All right, so that one is ready. So this one, what I'm gonna do is also start it at the chat CLI. But I'm gonna actually start this one in a different way because it's smaller. I'm gonna come up here to the chat CLI, and when I do the UI for this with the actual app, you'll just be able, it'll automatically recommend things based off your hardware profile. So you won't have to worry about this stuff. But we have the from tiered, which I'm not going to use. Instead, I'm going to just do it from NVMe. And so this is going to stream it and set it all up directly off the hard drive, off the SSD. And so here we go. Wow, keep in mind, I'm starting a 1.1 billion parameter TinyLlama. While down here we now have a 7 billion parameter model going through its own little hallucinations, waiting for a 72 billion parameter Qwen model to hallucinate. Oh, we got a core dump on that one. I'll have to look at that. Why? Data tokenizer, legacy arch, GPU 0. Oh, that's why, because I'm already running one on 0. So it doesn't like that. Yeah, I got that right. Tiny 1.1. There's a tokenizer. One, 1666, 25 free. What did I do? Oh, that's why. My bad. So that is my bad. So when you run this from NVMe, you cannot use the features flag for the CUDA because obviously if I'm running it right from the hard drive, I can't leverage the GPU or the memory. So it appropriately aborted and dumped the core. It's like, no, you can't do that. So here, this one, it's so rad. Oh, that's funny. I was like, what do I do? Yeah. So here, this one's gonna kick up. It'll be fine. So these ones are starting to get there. It looks like this has started and is almost hydrated. The 72 billion. We should start getting stuff from that. We can see here that now we're getting stuff coming out of, or at least hydrating the 1.1. So that was my bad. There's certain setups with this that it has to be correct or it doesn't work. And that's stuff that we'll address in the app, so you guys don't have to think about that. Or I should say, I'll address in the app, so you don't have to think about that. It's going to give you little warnings and stuff. This is significant. As you can see, I'm running a 72 billion parameter, a 7 billion parameter, and a 1.1 billion parameter model, all open weight models. But this is just on a computer. Because of how I've separated everything, because all this stuff essentially takes advantage of the processing system and the RAM in a very ambiguous way or non-specific way, it allows me to put it on anything. Cell phones, tablets. I mean, it's not even a question of, oh, will it run it? It's just a question of, do you have enough storage space to hold it? Because if you have enough storage space to hold it, not even counting RAM, right? Just from this NVMe setup, so you can see this one's already hydrated. This 1.1 billion parameter model is running directly off the SSD and responding with using, what are we at here? 4 gigs of RAM. 4 gigs of RAM. And it doesn't even need to use the RAM. The RAM is just a buffer cache that is set up because of the operating system. So the 7 billion parameter model down here, we have it leveraging the VRAM for basically as much of its weights of the models that it can put in there that's available to it. And once it hits the cap on that VRAM, it'll default to using the NVMe model and the RAM model, which will basically offload all that and it all works together. It's a little slower, but it is very functional. As you can see down here below, we have stuff coming out fairly quick, like note these, and it's working on its own thing. The 72 billion parameter model looks like, because I'm running the other two, is going to take a little longer than the usual 10 to 12 minutes to hydrate. Hydrate just means it taking the question and putting it through all the parameters to start thinking about it. So let's see. Usually if I turn those off, it kicks on pretty quick. But it's a lot of processing, right? So what this does is it takes these models that normally companies put out open weight because, I mean, really, if you want to run the new Thinking Labs Inkling, which is 970 some billion parameters, you have to have an NVIDIA data center. You have to have these big GPU systems and spend hundreds of thousands of dollars just to be able to run that and hold the weights. Well, what I've done here makes it so that if you just have a large enough hard drive, you can literally load that up and run it. And then if you have RAM available, you can load up other models and run them. And then if you have a video card available, you can load up even more models and run those. And these are, they are quantized, but I've done this with the unquantized models. They run really well. This thing is going to take a little bit. Why does that CPU look like that? It's just running, showing just the whole thing instead of all the cores. So I just did an update, so all that stuff is just. But you can see here, we have the Llama 1.1, and this is really most what anyone needs on a cell phone. This right here will run perfectly fine on most people's cell phones or tablets. I have all the back end set up too to where I can network this model and its output with these other models, and so we can begin doing things like multiple billion parameter model brain systems. And you might say, oh, this is cool, you're just building agents. But no, these are the actual models. These aren't the agents taking action. These are the actual core models. Oh, we got it done. I babbled enough. All right, so you can see here, 72 billion parameters done. And usually when I'm running these, as I've been testing it, this will probably take, oh, that was quick. It usually takes about 10, 12 seconds, but it seems to be running a little quicker right now. Nice. So it's thinking, and we can see too, if I pull up OBS and then we undo that, you can see that all those are running and they are maxing everything out. You can see that, oh, let me do it this way. You can see that we have right here our chat legacy. This is the large model. Oh, the large model right now, it's running at 91 gigs, right? Because 91 gigs is available. I have 125 gigs total, 128, but whatever. Here we have the small model, which is running its cache adjustable on the RAM. And right here we have the 7 billion parameter model, which is running 14 gigs on RAM. It's running 9.87 gigs. Right here you can see on the video card it's using. And this larger model is also using 24 gigs of RAM while it's using 91 gig of 24 gigs of VRAM while it's using 91 gigs of system RAM and splitting the workload between the CPU and the GPU. So this is what I look at, and this is homogenized architecture for operating, building, and running artificial intelligence systems.